All right, everyone. Good morning, afternoon, or evening, depending on what time zone you're in, and welcome to AABC's Tab Talk webinar series. Today's webinar will discuss pressure independent valve technology, performance and testing considerations. My name is Colleen McCain, and I'll be your moderator today. I'd like to go over a few housekeeping notes before we get started. We encourage you to submit questions at any time using the Q&A button. We'll be holding a Q&A session at the end of the presentation, but please don't hesitate to submit questions as they come up. The chat function is where you can make general comments and chat with attendees. If you happen to be experiencing technical problems during the webinar, please use the chat function to inform the panelists, and our tech team will assist you. Finally, this course has been approved for 1 hour of continuing education credit. After the webinar, you will receive an automated email with your proof of attendance. Additionally, if you are a certified TBE or TBT, our team will be uploading your certificates of attendance to your respective member portals for you. This will be completed within a few weeks. Here's a little bit about our speakers today. Bob Walker has over 35 years of experience in the temperature controls industry, working as a senior application engineer with a major controls manufacturer and a Kansas City-based consulting firm, designing temperature control systems and energy management upgrades. He holds a certified energy manager designation from the Association of Energy Engineers, is a lead green associate, is the vice chair of ASHRAE's TC 6.1 hydronic and steam equipment and systems, and is a member of SSPC 41 standard methods for measurement. And Bob is joined today by Brian Venn. Brian has 24 years of experience in the commissioning and test and balance industry. Ranging from distribution centers to clean room environments, his experience is across all aspects of commercial and industrial applications of HVAC pertaining to the MEP discipline. Currently certified by the Associated Air Balance Council as a test and balance engineer. Additionally, Brian is certified as a commissioning authority by ACG. So without stealing any more time, I'm going to hand it off to Bob and Brian. Guys, kick it off.
Thank you.
Well, thank you, and good day, everybody, wherever you may be. Going to start our presentation on pressure independent valve technology, performance and testing considerations. I'm going to turn my camera off just so I don't have any web issues here, but obviously I'm still here while we're going through this. And you can look at Brian the entire time if you want to make faces. So we hope that you get something out of this, and feel free to ask some questions there. So let's get right into it. What we're going to do today, we have a bit of an agenda here. I'm not going to dwell too much on the agenda, but these are the topics that we're going to be discussing. And let's start off with just a little discussion about valve and coil performance. Get back to the basics for just a moment. Hydronic coils have a decidedly nonlinear characteristic. So to effectively control this nonlinear coil characteristic that you see on the screen there, engineers design and propose using an equal percentage flow characteristic valve. You look at this, it's obviously a mirror image of the coil. I put the two together, and now what I've done is basically taken that nonlinear coil characteristic and made it linear to make it much easier to control with a linear control signal. This is what you're trying to get with a pressure dependent control valve, but more importantly, this is the characteristic you get with a pressure independent control valve. Now, to fully understand how pressure affects the output of the control valve, let's work our way back a little bit and talk about pressure dependent control valves. We know that flow coefficient is the sizing relationship between flow and differential pressure across the fully open control valve. And keep in mind, this is a shortened formula. We know there's a specific gravity constant that should be plugged in there, but since we're looking at water or water with glycol, typically we're going to be at 1 or very near 1, so that really doesn't affect our calculation that much. This is how we size all pressure-dependent control valves today with flow coefficient, CV. When you look at this formula, two things should come to your mind. If I have a valve with a fixed CV, as the differential pressure rises across that valve, flow is going to go up. And as the differential pressure drops across that valve, the flow is going to go down. Keep in mind, too, that the majority of control valves are oversized. I'm sure you know that from being out on job sites. I know that from sizing valves because there are only certain values of CVs for any particular valve. So when somebody's sizing a control valve, you always pick the one, you try to pick one with the CV closest to your calculated CV without going under, because once again, you need to have that full capacity to hit the design point, which again, you may only be at 1 to 2% of the time, but you certainly don't want to say, hey, this valve controls better. But on that exceedingly hot day, well, you had to give up a little bit to achieve that. The next few slides are testing that was done at the Iowa Energy Center, and Belimo got into the pressure-independent valve business, added pressure-independent valves to our valve line in 2003. And one of the questions that we would get a lot is, are these valves really doing anything? I mean, they look nice, but what are they supposed to be doing? Well, the Iowa Energy Center at the time did some testing between a pressure-dependent valve, a globe valve, which you see on the screen here, and a pressure-independent valve, which you'll see in a couple of slides. In this case, this globe valve had a CV of 1.6. And as you see, here's the pressure drop across the valve. Whoops, got a little ahead of myself. Across the x-axis and up the y-axis is the flow rate. So at a 5-pound drop, we're at about 1.2 GPM. Kind of consider, okay, probably the design point that you want for that valve. But notice what happens, and I'm going to focus on this 40% open line. Each of these lines represents the valve being locked open at a certain percentage. And if I focus on this 40% line, because that's a very common area, you're going to see a modulating control valve, primarily controlling in that 0 to 50% range once you get up to temperature in the morning. If we increase that pressure across the valve to 10 pounds, look what happens to my flow. I basically pick up about a half a gallon. Okay, so right off the bat, we know this is overflow. But let's think about it in this perspective. Half a gallon from one valve isn't that big of a deal. If it's only one valve, yeah, probably not. Probably leak that much in the system, maybe. Yeah, I mean, we're not talking about a lot of water. But what if this is a series of half-inch reheat valves? So this was a half-inch valve located in a high-rise building like a hospital or an office building, where you have a high number of those valves, and a fourth of them were sending us an extra half gallon per minute of water. All of a sudden, you've got a lot of excess flow that you're pumping, and it's not helping the system, obviously. So this is what we're trying to eliminate by the use of pressure-independent control valves. One other point I want to make when you look at this drawing, this plot is, look at each point that this valve is open. As pressure goes up, you definitely see a marked increase in flow. Now, the same test was run, but with the pressure-independent control valve. And look again at the overflow area. And keep in mind, we're using different scales for the flow rate, but that overflow is very slight. And again, as you look at this drawing, you notice that the lines are not perfectly straight. There is some variation. Every pressure-independent valve manufacturer that I know of states their accuracy as plus or minus 5% due to system pressure fluctuations. You look at these lines, and that's certainly the case. The idea being is that if I have 5, 10, or up to 30 pounds or more across this pressure independent valve, I don't want to see big swings in flow like we did with the globe valve in the previous slides. How does this translate more to the system? Well, continuing the test, they did a test which was a set point step test. And the idea of this was they started at a 56-degree set point and increased every 4 to 5 degrees the set point every 90 minutes. You can see by looking this, the left-hand side is the pressure independent valve. You look at the left-hand side, and those increases are pretty marked. You can see exactly where the increases were occurring. But look at the pressure dependent valve on the right-hand side. Not too bad at heavier loads, but when we get into that part load condition, 50% and under, now we just start oscillating and hunting back and forth, due in fact to the part that the valve is losing its authority at part load, and it's becoming an oversized control valve. So in this case, our overflow is basically a net overflow at part loads. Well, that hurts even more, as this graph is showing the flow going through the valves. It hurts even more when you consider your valve is going to be controlling at part load a lot more than it is at full load. That's what we're trying to accomplish with pressure independent control valves. Let's talk this title, evolution of the control valve. It sounds like we're going to be a PBS special. And I like PBS, but it sounds like a PBS special coming up. Let's talk about pressure dependent and pressure independent valves. In a pressure dependent valve system, you have a balancing device, you have a control valve. It could be a 2 or 3-way valve. You have, I'm going to say, increased labor to balance the system. You have to go out and balance the system. As we saw in the previous slide, when pressure changes, flow changes. All going back to the whole concept on how we're sizing and controlling these valves. Is there anything wrong with this? No. I mean, we know there are millions of systems out there doing this exact same thing. But let's look at a couple of things in this to kind of delve into it a little further. First thing is, pretty much everybody on this call will agree, balancing a system is time consuming. One thing you're not going to hear me say through this is that you don't need balancers with pressure independent valves. You do. Even though I have to admit, I have a lot of consultants that's one of the first things they'll say. Oh, I don't need a balancer. No. But in this case, as you know, there is a lot of additional time involved in balancing a hydronic system. Now, one of the things that helped along the way was the introduction of automatic balance valves. And I would imagine everybody on this call would agree with this statement. This was certainly a step up from the manual balance valve. But it's not entirely the overall solution, I guess I should say, because what an automatic balance valve is doing, it's limiting the flow. It's a flow limiter. So as the slide says, it limits the maximum coil flow. The big question, what happens when I'm below maximum flow? Well, let me put it this way. If I have this on a circuit that my coil needs 10 GPM of flow, yes, this will prevent flows from greater than 10 GPM going through the circuit. But as an article that was published in the ASHRAE Journal a while ago said, some flow limiting valve manufacturers claim that their valve plus a standard pressure-dependent control valve provides the same performance as a pressure-independent control valve. And I agree with this statement completely. It is not so. The flow limiting valve essentially does nothing when the flow is below design. That is, when the control valve is throttling. So you're still going to get the pressure effects across the control valve with the increase and decrease in flow. But the one advantage, I guess I'd say, you shouldn't really be getting more than the maximum flow you have set through that flow limiting device. But it is not the same as a pressure independent control valve. A pressure independent control valve, as you see here on the slide, you notice the balancing device has gone away. Instead, your pressure independent valve is serving as both control and serving a purpose of the balancing valve. It's not the balancing valve per se, but you don't need a balancing valve with this. If you have pressure. Oh,
And Bob, if I could jump in here,
sure.
this is where the verification now starts to come in. So for balancers, the traditional, well, I got to go out there and balance and set the valve. It just changes a little bit and possibly pivots. And we really become a verification of both installation and manufacturer delivery. So that in that regard, the balancer, to your point, is still required. But also to your point, the control valve now is going to work a little bit like a VAV. And if we change static pressure or in the system or the pump, then we may not have to go back in the time-consuming manner and rebalance everything. And I think that was your point earlier, Bob.
Yes, it is. It certainly helps on the labor side, but what I'm more interested in is I don't have the design flow changes due to pressure. Now, with the pressure independent valve, you don't need CV. So my tools of sizing control valves kind of go away because you buy a pressure independent valve based on the design flow. A fully open PI valve provides X GPM. You want one that matches what the coil is doing. And again, more importantly, it's constant flow at part load. Now, let me throw another question that I've heard a lot here. I've heard a lot that guys have said, well, gosh, this sounds really good, but I need more pressure drop across pressure independent valves. So I need more pump head. How am I saving energy if I need more pump head? Well, let's think about that a minute. Most pressure independent control valves, in fact, let me rephrase, all pressure independent control valves have a minimum and maximum differential pressure required across the valve, which you can measure in this valve in particular by tapping across the two ports. We and most manufacturers will say that the minimum pressure required is a 5 PSID. Some companies, are self-included, have product that will be require less differential pressure, but you also don't get as much flow from the valve. They're derated, so to speak. But as a general rule, everybody's looking at about a 5-pound minimum differential pressure. So I hope that in the past, guys were putting in modulating control valves with a 4 or 5 pound drop. I know that wasn't necessarily the case, but again, to get some authority of that valve, you want some pressure drop. Well, I was looking the other day in preparation for this, and I know this was a question I asked Brian before. I said, well, how much pressure drop do you need across a balancing device? Well, I looked at some of the common auto flow devices, and the pressure requirements across them ranged from 1.2 to 7.3 PSI. So I'm going to put in a pressure independent valve that requires 5 pounds. I'm replacing a control valve modulating that requires 4 to 5 pounds. And I'm eliminating that auto flow device that could take anywhere from 1 to 7 pounds. I don't see where the 5-pound pressure independent valve is going to be that much of a hardship on your pump head. The devices you're taking out has some pressure requirements as well.
And Bob, from a tab standpoint, the maximum amount of pressure that we need or want is only enough to get the GPM we want, because our job is to get the pumps running as low as possible for the owner's energy recognition of their design.
Exactly. Pump energy equals dollars. So it's a consideration, but it's not I need more pump head. I know I was on jobs in the beginning of this. We started with PI valves, I think, as I said, in 03, that we didn't have 5 pounds out there, but the pumps were set so low by direction of design that even standard control valves weren't going to accomplish much because there was no pressure drop. PI valves supply a specific flow for each value of the control signal, regardless of the pressure variations in the system. Seems simple enough. So we're going to talk for a moment about the 2 different types of pressure independent valves. On the screen you see right now are some examples of mechanically regulated pressure independent valves. These are all considered 2-chamber devices, because you have a control valve and some type of pressure regulator or cartridge regulator. Okay. Adjusting the flow can always be done out in the field. I'm going to go through what we do and then bring up a couple of other things that I've seen from other manufacturers. For our pressure regulated product, it's just a matter of adjusting this clip position to match where you want the flow from this valve. On this particular model, the valve itself will produce 1.9 GPM fully open. But I can, by a matter of clip positions, take the maximum flow down to 0.2. In this example, we have it set for a 0.4 GPM, which is a clip setting of 3. All the flows are adjusted by limiting the opening, the opening of the valve, the span of the opening, I should say, the span of the actuator and the opening of the valve, better way to say it. I'll get it out yet. Some companies use a dial setting, perhaps under the actuator. Accomplishes the same thing. Some of our older product from back in 2003, these settings were done with electronic stops programmed in the actuator. But in all these cases, it's all field adjustable. They can be factory set, but they can also be field adjusted. So there is no big change that needs to be made if you want to adjust these. One other thing I wanted to bring up, I get this question a lot. Well, what do I do if I'm flushing? Well, my advice to you is to verify with the manufacturer their requirement. We don't have a requirement to make any change in the valve when you do a flush. I know there are some companies that will say, okay, take the setting the valve is at and move it to this position for a flush, and then move it back to the set position. So that's something you need to look at with each manufacturer. I know we've had products since 2003, and we frankly haven't seen any big issues with bad water and in flushing. And I know nobody ever tells me they have good water. Everybody always tells me they have bad water. But you know, I had one instance where the valve was full of gunk and the strainer was perfectly clean. Seemed a little odd. The valves are pretty durable. In our case, we have a 0.5% failure rate over the course of the life of the products. So dirt and grime, as I like to say, there's a lot of dirt and grime and bad systems out there. And at least from our standpoint, the valve is pretty doggone durable. I made on that previous slide, I had a comment about Venom and Vmax, and I want to discuss this just briefly. And these are Belimo terms, but every manufacturer has some translation of these terms. Venom is telling me that's the total capacity and flow that a valve can produce. On that example I had, 1.9 is the maximum flow I can get out of it. Vmax is the setting that says, I want Vmax to be set based on the coil. If I have a coil that's 1.4 GPM, I want to set that valve so fully open, it's 1.4 GPM. You're going to hear me come back to Venom and Vmax in a little bit, but again, it's the nominal flow of the valve and the maximum set value of the flow.
And Bob, if I could on this one, this is also, again, leading into the tie between kind of comparing this to a VAV, right? With a min and a max reading and a full open reading, but being and having the ability to change a factor or an orifice and actually control in the field the readings that you're getting.
Yes. And I have a couple of sites coming up. We're going to talk about how to adjust that, but it is, I always like to say, it doesn't take us long to adjust the settings as it does to get the ladder and get up to the product itself. You know, always one of those situations. Oops. Let's talk about flow verification. Good point. Everybody always asks the question, you know, how can I go verify the flow? And frankly, I have to tell you, for a two-chamber device, there is really no excellent way using the device itself to verify the flow. I can tell you from our own experience, if I wanted to read a pressure across this device and translate it to flow, I would need to have a PT port in this area. Now keep in mind, this is reading the inlet, this is reading the outlet pressure across the device for verification of that 5-pound differential or whatever it may be. Trying to read this pressure is basically impossible. It varies too much. It is not a stable pressure reading. For many years, we published that, yeah, if this pressure is between X and Y, you're good, but you couldn't translate it to a flow reading. I'm going to show you a solution to that here in just a moment, but a lot of this depends, and you're going to hear me say this a lot, depends on the requirements of the project. What does the engineer want to see in a report at the end of the day? And it goes back to what Brian had mentioned a moment ago with verification versus balancing. So how do you test the flow of this? Well, years ago, we got with some balancers, and I'm just going to state the comments here because everyone has a pro and con. And we were told at a time, well, you should use an ultrasonic flow meter to verify the flow. Not even going to get into that discussion. I mean, does everybody have one? Can you get a good reading? You know, there's a lot of variables there. But total flow verification, air temperature differential at the terminal units, the water temperature differential at the terminal units, pressure differential across the coils. There's a wide variety of ways to verify flow. Unfortunately, you just can't walk up and tap into it. Now, there are options. We have them too, where you can put a calibrated orifice in a piping package with these devices and have something like that to verify the flow. I'll be honest, we don't sell a lot of them. You know, it's not really used a lot and recommended by a lot of people because, of course, that adds differential pressure across the project as well. So we addressed back before 2010, we realized one of the challenges with pressure independent valves, especially on the larger sizes, were they were expensive, relatively more expensive than a typical commercial HVAC project would see. So we looked at ways to address this, and what Belimo developed was what was called an electronic pressure independent valve. And again, as you see here on this drawing, it includes the control valve, in this case, an ultrasonic flow sensor, and a smart actuator. There's software built into that actuator. So what is this doing? Well, let's talk about the flow meter first. The flow meter is accurate to plus or minus 2% with 0.5% repeatability. The whole concept here is we have two ultrasonic transmitter with the emitter receiver, and then two acoustic mirrors. There's also a temperature sensor that in our case is used in the logic to compensate for water temperature changes and to calculate and compensate for the glycol compensation. An important thing. You look at this flow meter, there's no moving parts. We design our products to be maintenance free. You don't have to go out and maintain these products. On top of it with the flow meter, unless if there was dirt an issue, which it's not with the ultrasonic transit time technology, or we're not using a turbine for this, what's the one variable that can change? The fluid. If you're using glycol, we all know that glycol isn't the same from the day the job started as it goes down the line. So this takes care of that one variable that's out there with that issue with using ultrasonic flow meters. So using transit time, the flow is calculated. Now,
And
where
Bob,
does, yes.
I'm sorry, if I can throw in here, a lot of the test and balance folks in the audience are used to using clamp-on ultrasonic meters. And that has been probably in part the difficulty that you were referencing earlier. And to clarify in this, most balancers do not have in-stream access to ultrasonic measurements. And that's really the fundamental difference of why this ultrasonic is probably going to be a lot more dependable than the ones that we're actually using and referencing on the outside of the pipes.
Exactly. I know I've heard a lot of horror stories about the clamp-on ultrasonic meters. You can't get a good place for the plate. You don't get a good reading. Well, in this case, it is an in-stream device, which certainly helps immensely with that. You see here again, whoops, there we go, the VNOM and the VMAX. Think about this as we head through some of this other discussion. The electronic pressure independent valves have the capability of being programmed either for a position control or a pressure dependent mode, like a globe valve, and flow control mode, which is a pressure independent mode. Simply put, in position control, if my control signal has a 50% control, let's say I've got a 0 to 10 volt signal. So if I go to 5 volts, that actuator is going to drive that valve 50% open, regardless of flow. With flow control, it's going to drive the actuator to the calculated flow rate in its rotation based on the actual requested flow rate. So let's say it's a linear valve. In my example, I had an 80 GPM valve. If it's linear and it gets a 50% signal, that valve is going to position to provide us 40 GPM of flow. Pressure independent takes into account that as pressure changes, the flow can change. Position control is just straight out. Here's the physical position we want to drive the valve. Now, I mentioned before when we were talking about this, that we do have devices, you can make adjustments in the field. For Belimo, we have a handheld device that, as you can see, plugs right into the actuator. And I'll show you a couple of pictures of this in a couple of slides. But there's also the capability of doing software on your laptop with the Belimo PC tool. Frankly, for what you're doing out in the field, the ZTH will show you the flow from the flow meter. The ZTH will allow you to change the flow. It will allow you to toggle between pressure independent and pressure dependent mode. And I'll show you that, why you might want to do that in a moment. But the bottom line, the majority of what you can do with that handheld tool. Off of the PC tool, a couple of things you can do is the valves come shipped as equal percentage. If you want them in a linear form, a linear characteristic, that would be a PC tool application, that type of thing. If you have anything like that, let us know. We can help you do that. That is not a major problem, to say the least, to make that change. One thing I do want to talk about is control signal adaptation. And you look at this picture of the Belimo actuator, and what you see is there's a little light, it looks like, that says adaptation. It's actually a push button that you need to use a screwdriver or a pin or something. The point is, whenever you make a change to the maximum flow, regardless of what that change is, you should hit adaptation of the actuator. That will reposition the flow across your full control signal. It basically drives the valve in both directions and then goes back to the control position based on the control input signal. So in my example, I have a 2-inch EPIV with a VNON of 100. So at 10 volts, fully open, it's going to pass 100 GPM. But if I've readjusted my Vmax to 80 gallons, after I adapt that assembly, now 10 volts is equal to 80 GPM and not 100 GPM. So you don't lose your control signal resolution by adjusting the travel of the valve / actuator. So this is probably the question, why you need to know all this? Well, it goes back to what Brian mentioned a few moments ago. PI valves don't need to be balanced. They need to be verified for proper setup and operation. More importantly, somebody should check. If you get them from the factory, they can be purchased, tagged, and preset with the proper Vmax. But we all know box of 1/2-inch valves, they may or may not get put in at the right coil. So verification is proper. Depending on the consultant, verification may include, specifications. Verification may include verifying you have a 5-pound differential. There can be many levels of verification. This kind of goes back to control mode. If the control contractor just wants to verify that his control signal is tracking, putting the valves in position or non-pressure independent mode allows that. You watch the actuator and it will go the full span. If I go to flow control, now it's going to be controlling based on flow, which may or may not exhibit full span. I know in the beginning, got a lot of questions about, hey, your valves aren't working. They're not opening up fully, depending on where they're set. You're absolutely right. They may not be opening up fully, but they're working fine.
And Bob, this is where we actually ran into that when we first came across these valves. And as field verifiers, in this case, we needed to learn how to work with a new technology, right? And we really needed to dig into the cuts and understand that it was factory set, and it was a reason it wasn't going to full open. But we didn't understand it until we really dove into the technology. And once you do that, there is a little bit of a retraining to your workforce on the tab side to adjust to this, but we're constantly going to be doing that as technology evolves anyway. So for us, we had a couple of hard learning lessons, but then we were able to understand the valve after 1 or 2 jobs. And now they're a welcome sight, because we are not losing our traction as balancers. We're still verifying. And when troubleshooting occurs, we really are the experts there to figure out what's going on anyway. So it's a good measure to still have trained tab folks doing the verification.
Yes. The ZTH tool that you see here, and just a couple of pictures of it to show you, but as I said, tells you what that programmed Vmax setting is. You can adjust it. You can tweak that flow to where you want it. It will also tell you one of the things, what's the flow as read by the flow meter, and what the set point is. So if it's set, if it's supposed to be going, in this case, it was supposed to be hitting 88, and the volume was actually 89 gallons per minute, well within 5%, but you can read the flow. To me, that is one of the huge differences with the EPIV, beyond the cost advantages. The fact that you can actually read the flow directly is really a nice feature. Quickly, I just want to touch upon how these valves work. The mechanically regulated PI valve, simply put, flow is going to come in through the right-hand side. You notice there are 3 pressures. P1 and P3 is that differential pressure across the whole device that's required for the valve to be pressure independent. P2 is the pressure after loss going through the regulator, and P3 is the loss going after the pressure after the loss going through the valve. I'll get it out in a minute. The force from P3 pushes the regulator open, P2 pushes it closed, and the whole idea, remember, with pressure-dependent valves, as pressure goes up, flow goes up. Well, in this case, as pressure goes up, the regulator adjusts to compensate. So our output flow is plus or minus 5% due to system pressure fluctuations. With the electronic PI valve, you feed your control signal into the product. So the smart actuator is getting the signal. Programmed into this is the valve curves. The valve compares, whoops, that went a little fast, compares the actual flow that's occurring across this valve. If the flow is greater than a 5% tolerance, it will reposition itself back to go within a 1% tolerance. So again, what it's doing is knows where the flow should be, where the flow is, and adjusts the actual flow, which in turn is compensating for the pressure variations across the valve. Or as Brian alluded to a moment ago, it's a pressure independent VAV box for water. Same concept, same sequencing, just 2 different mediums. One thing I did want to point out, everything we have today is an ultrasonic flow meter. In the beginning, our larger product used a magnetic flow meter, as you see here. Same advantages, same accuracy, 2%, no moving parts. But one thing I do want to point out to you, and we ran across this a few times, flow in this case should go across from one nub to the next, and not the flow, in the case of my picture, you hitting it directly onto it. Because the whole idea of the magnetic flow meter is that the flow is measured by changes in an induced voltage that's generated by this conductive field. So if the fluid needs to be going across it at those 2 points. Again, there's a lot of product out there that has that. You're not going to see it on new product anymore today. This is just a pictorial to show you the whole concept. The black line being the programmed curve of the valve into the actuator, the plus minus 5% and the plus minus 1%. The valves do have linear curves built into them as well, if you can call it a curve. The linear characteristic built into them, those can be changed if you so need it for instance, a bypass application. Just a couple of quick things, installation considerations. You definitely, for our product, you need 5 straight pipe diameters before the flow sensor. No straight pipe diameters after. If you have less than 5, the valve will still function. However, you're going to see that accuracy rise quickly from plus or minus 2%. So definitely the case, get those 5 straight pipe diameters in front of it. Second, so when you're doing verification, that's something to look out for, definitely. Second thing, how do you install it in the pipe? Well, just like all electronic valves, I don't want the actuator below horizontal. You don't want condensate to be able to roll back into the electronics. You can mount them vertical. I see a number of these valves mounted in vertical runs because it's much easier to get the 5 straight pipe diameters, but it doesn't matter. Flow can go up or down. It's not going to affect the flow meter in either way. So I've come to the end of my slides, and I'm sure there are questions.
Yes, we do have some questions, but before we move on to the questions, we are going to quickly move to a short message from the sponsor of today's webinar, Field Inspections Plus.
Okay.
Field Inspections Plus flagship product Clipboard is designed to help tab professionals do their job efficiently and effectively. Our software is designed to help you collect data, both online and offline, across all kinds of devices, help you easily manage your projects. All the data is stored up in the cloud for easy access, and most importantly, generate industry standard reports that can be reviewed and certified within hours, depending on the size of the project. So check out fieldinspectionsplus.com and start your free trial today.
All right, great. Thanks so much, Bob and Brian. We are going to move into our Q&A portion now. All right, so first question I have here says, when checking the differential pressure across the valve to determine that it's within range, how then does someone verify that the correct cartridge is installed in the PIC valve? Sometimes it's hard to double check which cartridge is installed.
Bob, did you want to grab that one?
From our standpoint, well, we're not using cartridges, but obviously, you know, we have different ranges, say for the 1/2-inch valve. A lot of it, in our case, what you need to look at is the tagging on for us, the tagging on the valve itself. Each of the valves is tagged, which would give you that information.
And from a balancing side answer, you know, we definitely run across the tags either being wrong, or sometimes you'll see them restuck to the valve. So, you know, somebody maybe pulled it off and we get there. If we're trying to verify that the cartridge is working correctly, we'll fall back on our AABC training and we'll go right to a delta T method if temperature is available on the system, or we'll look at the delta P of the coil, right, and compare that to the design rating. So, you know, that would be other ways to fall back on trying to verify whether or not that cartridge is correct. Without having an x-ray machine and being able to look inside and open things up, those are really the only ways to verify that I'm aware of.
All right, next question. Have pressure-independent valves made reverse return piping configurations entirely unnecessary, or are there instances where the two can be employed in a complementary way?
With the idea that the reverse return system is quote unquote trying to equalize the pressures, pressure independent valves really, in my eyes, have eliminated the need for reverse return piping. You know, the whole purpose of reverse return was to equalize the pressures. So you hopefully didn't get these big surges in pressure across the control valves. Well, it's kind of to me, it's an easy justification that a PI valve doesn't require you to use reverse return piping and the additional cost of reverse return piping. But Brian, I'm going to let you answer from a TAB's perspective.
Well, again, I'm not a PE, so I'm not going to say that I'm going to be responsible for saying it's eliminated, but it certainly does take some of that that issue that you have to put into the design out of the equation, right? And it does, in a way, simplify some of the things that design engineers will be looking at when figuring in a reverse return system.
Okay, next question. For Belimo energy valve assemblies, do those use PIC valves?
They absolutely do. For the Belimo energy valve, it's based on the EPIV.
Okay, next question.
Hey, Colleen, I can see the questions too, and I actually see a good one. And it has to do with recalibrating or recommissioning, Bob, of your valves. Is there anything that you recommend as a, biannual or every 5 years that these would ever have to be recalibrated or recommissioned?
We do not. Again, our design level is we want to design product for no maintenance. I'll put it this way. I think it falls back into the whole system. Do you want to recommission the building to make sure that it's operating as designed? Yes, but individually for our product, it's not required.
Interesting. That was a question I had, so I was glad to see that pop up in there. Sorry, Colleen, go ahead.
No, you're fine. Thank you. All right, next question is painters need to be told they need to protect the dial positions too. Many get painted over and it's easy to damage the dial and chart fixing.
I'll take
I'm
this
not
one.
going to respond to that. I don't want to piss off any painters.
I'll take this one as a guy in the field. I'm pretty sure it already says that in the painter specification, that you're supposed to take care of other folks' work, just like we're supposed to take care of the insulators' work, right? We have a responsibility if we disturb their vapor barrier that we should in turn repair it and put it back in the condition we found it. But I'm pretty sure that already existed as a call out in the painter spec. Great question, though.
Yeah, it is. And we've all seen it. So
yes.
It's true.
Okay, great. Next question. Okay, we have encountered some projects where PIC valves are installed with manual balancing valves and have compared the rated flow on the PIC valve to the reading on the manual balancing valve. In some cases, these values have diverged by 20% or greater. If both devices are installed and operating per their manufacturer's instructions, what could account for this discrepancy? What should we report?
Want me to take this one, Bob?
Yeah, go ahead. I want to hear your answer.
Sure. So there could be a couple of reasons. One of them is the valve actuator moving while you're still reading? Are you reading them simultaneously? Making sure that while you're taking that data that they are both in solid state, not moving, right? So that's a baseline for comparison. Secondly, again, falling back on the AABC training, I would take those numbers. Anytime we get conflicting data in the field, we want to go get another reliable data point to compare it to. So we would fall back on the manufacturer's delta P of that coil, right? And start to compare it to that as well, to give us maybe a clue into either the circuit balancing valve is the culprit that's not reading accurately, or the reading that we're grabbing based on pressures across the valve body is not reliable. But looking for other data sources to help you weed out which one may be the faulty reading would be how we would handle that.
All right, thank you. Okay, next question. What's the accuracy of the ultrasonic devices?
Plus or minus 2% with a repeatability of plus or minus 0.5%. And they are all wet calibrated before they leave the factory.
All right, great. Next question. At what level or degree does it become a concern that the flow sensor isn't reading the right flow?
Trying to read into this.
Can you actually say the question again, Colleen?
Yeah,
I
sure.
didn't catch all that.
At what level or degree does it become a concern that the flow sensor isn't reading the right flow?
Degree, I wonder if that's degree based on temperature? Is that how you're understanding it, Bob?
No, way I think I'm understanding this is you're out on project, you think the flow sensor isn't reading correctly. At what point do you feel like that it becomes an issue? I think a lot of, I guess in my mind, a lot of that would come to the point, okay, you're testing it another method, let's say across the coil like Brian suggested, and geez, that's reading I'm 50% off. There's something wrong here. I would think that type of thing. I mean, again, I know our flow meters are tested before they leave the factory, so I'm confident in those. But if I told you, you know, like I said, we do have a failure rate, and if I told you everything was perfect, I'd be
Well, I was
lying.
about to say, you know, Bob, that could play also into human error. Your example of half-inch valves coming out of a box and maybe going in the wrong places, right? You know, if you are out in the field and you do start to sense that this valve is incorrect, I would say, especially if you're an AABC field technician, trust your gut. Back it up by collecting other data, like across the coil, but then I would reach out, and Bob has been more than open during this whole process, call Belimo, right? And ask them about the valve body that you're seeing. And more importantly, maybe reference it against the schedule of valves in the drawings and look at some of the other air handlers to see if you can detect if maybe it was installed at the wrong air handler and it truly could be reading wrong, right? Because that would be a human error field installation issue.
One thing I'll throw in here real quick too, you can go on our website, and on our website is a contact area. I'm one of a team of regional application consultants. So, you know, you can certainly call our 800 number, but you can contact us. You can search by your location. If you have questions, feel free to contact us. That's what we're here for.
Thanks, guys. The question asker did say that you guys nailed it, so you're good. Thank you.
Thank you.
Good.
All right, the next one. I have had design engineers ask what is the pressure drop across the valve, even though they'd spec'd the pressure independent control valves. I explained that there is not a CV associated with the valve, so I cannot calculate the final delta P. Any advice on how to respond?
I would look at the manufacturer's product, say for Belimo, and say 5 pounds. The minimum pressure drop required for the pressure independent valve to be pressure independent is that magic number. He's probably asking in association with this pump sizing. But, and frankly, we still get that question some. And if you still can't get over that hump with the design engineer, feel free to get us involved at Belimo. Most of my time is spent talking to the design engineers, so we're here to answer their questions.
And I have a side from the tab side of that. We would write a detailed note in our executive summary about the valves that were chosen because the engineer approved them, right? So he should know the valves that he chose, right, and how they perform. And we would then also report the delta P across the coil in the state when we balanced it as a backup. Because to Bob's point earlier, we can't, without having 3 ports, accurately report that number, right? And as a tab guy, one of our principles is it repeatable? Is it reliable? Right? So we have to be able to go back and set that back up. And a way for us to do that would be to verify that we had the delta P across the coil, even if we can't report the delta P across the control valve. Is that probably also a good way, Bob, to handle that?
Yes. Yes.
But it definitely needs to be addressed on the tab report. And if it's not, it could be because maybe some of the tab folks don't necessarily understand the technology yet. And that all goes into training, right? And that's really why we at ABC fall back on training as our pillar, because if we're sending folks out there, we could actually be generating reports that actually generate more questions rather than answer them in the long run. So having a good standard note or a summary note that's going to go along with a new type of technology or a valve you're seeing in the field is absolutely needed to be in your deliverable or your report.
And again, I'll just throw in too, I know AABC is excellent on the training side, but if you're a balancer and want training on our product and want training, feel free to contact us. There's no charge for it. I know, which is kind of scary when you think about it, but we've always had the policy of training is free. We want to make you comfortable. Frankly, we want to make you comfortable with the product, because the more comfortable you are, you don't call as much except to order. So it works out really great from our standpoint.
All right.
All right, thanks, guys. I do see a lot of people are still logged into the webinar. That's great. Thanks for sticking around. So we're just going to continue with the Q&A. There's great questions in here.
Great.
All right, so the next one up is, how are the EPIV valves less expensive upfront? Also, shouldn't they be less expensive over the life of the equipment because they will have a lower pressure drop?
I like this question, especially that second part. Yes, you're right. Let's talk briefly about cost. If I look at the raw cost of any pressure independent valve versus a pressure dependent valve, yes, the pressure independent valve, material cost, valve for valve, the pressure independent is going to be more expensive. In some cases, not as much as you would think. But when you start factoring in other factors, such as, I don't need a balancing device. So on a new job, I don't need a balance. I'm sorry, I don't need a balancer. Well, there goes. Thanks for letting me be here. You don't need the mechanical to buy or install the balancing device. The balancer, it's not as time intensive. I think Brian's referred to that before. It's a less time consuming activity. So when I put both those things together, what I've seen, if you have a typical job with more 1/2 inch than 3/4 than 1 inch valves and so forth, you get lots of savings on those 1/2 inch valves. Yeah, that 4-inch valve is probably going to be a little more expensive, but you shouldn't pay any more for a pressure independent valve on a normal job. Now, if you come to me with all you want is 6-inch valves, yeah, you're probably going to pay more. But so, and your second point of the question is excellent, because there are savings with the pumping, sometimes substantial savings with the pumping, and that all contributes back to your central plant. On our website, we have some estimators that you can throw in some basic information and actually do some quick calculations as to what PI valves could save you on a project. So a good question and good insight there.
Mm-hmm.
All right, great. Next question. Can we connect these valves to the BAS system to view and monitor the flow rate continuously on the computer?
For the EPIV, absolutely. I'm sure many of you are familiar with Belimo. Typically, the feedback signal on the Belimo actuator, the 5-wire, tracks the clamp position over a 2 to 10 volt output. So if the actuator traveled 90 degrees, it could be 10 volts, travel halfway, it's 6 volts, that kind of thing. On the EPIV, that is actually tracking the flow meter, the output from the flow meter. So you're absolutely right. You can take that signal as an input to the BAS system and be tracking the flow in real time. So very easily done, and a lot of folks are doing that.
And if I could throw in here too, as we're comparing it to VAV systems, once we have confidence that we've verified flow at all these valves, and we want to start to squeeze more energy savings out of these systems, changing pressures at the pump and experimenting becomes so much easier. And that's where Bob is saying the savings and recognizing the savings in labor costs. Because if that was a constant volume valve, the entire system would then need to be reset at a lower pressure, right? But because we have these valves, we can actually lower the pressure, go back out and still field verify, in some cases very quickly, by looking at the PSI across certain coils in the system, and watch it still performing at maybe 5 or 10 hertz less at the pump. Now we're starting to be able to even start to do virtual testing, like being able to have that virtual twin building where you want to manipulate things, but you don't want to mess up. Well, now we can actually do that in the field because it's not so labor prohibitive, because we don't have to mess up 9 stories of a hospital and rebalance everything. We've already verified everything on the front end, and we can really start being those energy experts and improving maybe even on the field performance as a team out in the field.
All right, thank you. Next question. How would this system determine the needed flow set point when it is to control the air temperature that coil controls?
Well, in short, if it's a new project, so you have submittal data, you would basically look at the submittal data for the coil, and that's your Vmax. Because, the coil's going to have, in that submittal, it's going to tell you what the design GPM is, the design delta T, and the like. So that's what I would use. If it's a retrofit job where you don't have that information, and I understand, then you got to do some creative thinking, because you don't want to set Vmax so low that you cap off flow that the coil could take. But I guess the short term, you want to have Vmax, that flow setting, to match what your heat transfer device, what your coil needs.
All right, great, thanks. Next question. What kind of feedback is made available for the EPIV valves to know when the ultrasonic flow is not reading properly? What is the general failure rate and life of those sensors?
There are some internal alarms on some of the products that will tell you if there's a flow meter error, too many bubbles, that type of thing. But frankly, the easiest way I have is that if your flow reading is, you could see it and say, hey, I know we have an issue. It's reading 0, or it's reading, it's reading the same flow forever and ever and ever. So
can it be installed backwards, Bob? Could it read negative?
Yeah, that's a good question. I don't have an answer to. I believe when it's installed backwards, though, it's just going to read 0.
Okay.
But I have to check on that myself. I haven't even thought of that. And that is one important thing. Please don't install them backwards. They don't work well. There's an arrow on them.
Well, and to your
Through the
point,
flow
with
meter
with the old magnetic sensors that you showed us, we ran into an issue on a job where they were all installed perpendicular to the flow instead of parallel. And that ended up being our issue on all of those sensors. So very important that things are installed properly.
Okay, next question.
I'm sorry. Can I go back?
Yeah.
I didn't answer all that question. I'm sorry. I'm
Oh,
looking
absolutely. Yes, Bob, go ahead.
I only answered half of it. What's the general failure rate and life of those sensors? I can tell you again, we see a failure rate of less than 0.5% of 1%, and the life of the sensors, We've got them installed since 2010 and they're still working fine. So, you know, we're trying to design out for a number of years on the flow sensors. Now I'm
Okay.
done.
All right, perfect. Moving on to the next question. In the case of the three-way PIC valve, would the PIC valve automatically balance the bypass, or would you need an additional shutoff for balancing valve?
All right. To make it simple, and I know what you saw on the slide, so I'll go back to that in just a second. There is not a three-way PICV. Because I'm getting ahead of everybody, but the next question was, in case of having 3 ports, how do you measure flow? It would be hard to measure flow with a 3-way PICV. The picture you saw earlier, and I didn't mention it, and I knew as soon as I got off, if I knew I should have said something. That is a specialized 6-way valve that is pressure independent. 6-way, think of a you know, chilled beam system where we're operating hot and chilled water. So when the valve cycles through its control, it's operating for both the chilled water and hot water side, so to speak. But I've seen some people trying to do 3-way PICVs. But I've really never seen any out in the marketplace, just for the reason of the second question. How do you measure flow if it's a 3-way valve?
Okay, thank you. Let's see, the second to last question here. In case of having 3 ports, how do we measure flow?
Oh, I got that already.
Oh, you did? I'm so sorry.
That's okay.
Okay,
I
so
got
here we
ahead
go.
of you.
No, you're fine. Thank you. Can the flow sensor be factory calibrated or different mediums other than clear cold water like 30% glycol?
Right now, the electronic PI valve is designed for water and glycol, either ethyl or poly. It's good for up to a 60% glycol mix. If you have a system with glycol, what you basically have to do is there's a toggle in there that you select what type of glycol you have, and it takes it from there.
All right, great. Okay, now last question we have here. How does the CX agent confirm flows with the tab agency? What criteria on the PI should show on the tab report?
Brian?
So that goes back to that other question of, you know, having an executive summary and some good notes. In the absence of what a lot of design engineers are reviewing these tab reports are used to seeing a given delta P across those valves, right? That they could set on a traditional wheel or chart. So without that, you do need to fall back on the numbers that you can repeat, which is showing the delta P across the coil, showing the delta T across the coil. And sometimes, if necessary, having an ultrasonic meter reading to back up if you're given enough straightaway and that type of condition. So, you know, there's not a set pressure number that you can put in that traditional column. It really does need to be handled with a note and then some other backed up data from the coil.
All right, perfect. Thanks, everyone. Those were great questions. And that's all we really have time for today. We did go a little over, so thank you to everyone who is still on and joined us today. Bob and Brian, thank you for coming on to share this valuable information with our membership and non-members who joined today. I would also like to thank our sponsor for today's webinar, Field Inspections Plus. And our next webinar here, you can see up on the screen, is lined up in our series, is about the future of tab, set for June 23rd. So make sure you mark your calendars. And if you enjoyed today's webinar, go ahead and view our website, aabc.com, to see a full list of our upcoming schedule and register. Lastly, as a reminder, attendees will receive an email within 24 hours of your proof of attendance. Have a great day, everyone, and we'll see you in June.
Thank you, Bob.
Thank you, everybody. I enjoyed it.
I did as well.